Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we will continue our learning on, Sapphire module in Kappa software, Kappa workstation. It's about pressure transient analysis. And now we will perform numerical modeling, all right? Numerical pressure transient analysis. So let's go ahead. Let's start a new file and it's blank. All right. Okay, so let's make numerical horizontal well, and then fractured like this, horizontal, fracture. Okay, and then well radius, for example, 3.06 inches. Pay zone, let's say it's a hypothetical case, 50, with rock compressibility, let's say 2.6 to the power of -5. Sorry. Right, 2.6. And then porosity 0.23, for example. And let's say reservoir depth 3,550. Okay, and then we go to the next. All right, so for this PVT, multi-phase, and then an advanced PVT must be designed. An advanced PVT must be defined. Okay, click on this. All right, let's maintain everything here. For the gas properties or saturated oil, this oil properties, and then interfacial tension. Let's keep it as it is. All right, and then relative permeability. So for this relative permeability, let me go back. By the way, you can change the multi-phase from oil to gas, right? Fluid system, we include water here. So saturated oil, bubble point fluid, water, we include water. So once again, you need to provide the oil property. All right, the gas property as well. And of course, water property. In this case, I will use as a starter 10,000 ppm for the salinity. Okay, and then click on OK. Now the relative permeability for multi-phase case is activated. Let's enter this. Okay, so now for water oil, let's say the residual water is 0.46 and residual oil saturation 0.17, and let's say this 0.63, and this one, for example, 0.05. Okay, and then KROW model, for example, you can use exponential or power. Okay, and then for this, we will use stone to modify it, but you can also use another method here. For gas, 0.02, for example, 0, and then this one, 0.63, just a hypothetical case for learning. And this one is 0.19, for example. Okay, and then, yeah, you can refine this, relative permeability. Okay, so this is for the water oil. We can also change the exponent like 1.5 and see what happened there, right? And this is for oil and gas. Check no extrapolation. Okay. So you see the difference, right? And this is the three-phase relative permeability. Okay, so by the way, you can also load for, relative permeability table if you have. You can provide table of relative permeability and use it for your real model here. But let's leave it as it is for now and click on OK. Okay, and then we click on next button. So formation volume factor, let's say 1.23, for example. And then for the viscosity, 0.68. All right, and for the water saturation, so for the water saturation, 0.46. All right, and then for the total compressibility, it's, calculation, right? 0.46, 0.54, it's 0. And then let's input. And then let's input the compressibility. Let's say for oil, it's 4 to the power of -5. And then this, for example, 0.00105. And for the compressibility of water, it should be small. Let's say 3 to the power of -6. The saturations input above may be inconsistent with later initial state values. Okay, you can also reset all from PVT. All right. By the way, maybe we can, as it is just a learning for simplicity, let's reset all from PVT. Click on OK. All right, so that's it, more or less. And then, by the way, let's check once again. Or maybe I'm going to use instead this to the power of -4. Quite compressible. Okay, and then this should be to the power of -3, let's say. Quite compressible. Click on OK. All right, and then so we can move further. Next. Step 5, first analysis, numerical parameters. Yes, vertical anisotropy, check that. You can also use real PVT if you want. And you can also allow aquifers. Okay, so for now, we continue first. Next or create. All right. Okay, so we will not, analyze the real measurement, the real test, but rather we will design this case using numerical method. All right, so from here, we can start from map, actually. So we will draw a case here. Okay, so first test that well, double click to enter the well, and then name, let's say horizontal well, and you can also input the ID. Let's expand this window. Let's say to make it more complex, it's horizontal fracture and the symbol is like this. Okay, so geometry and properties. Modeling type, let's start from simple, of course. Drill floor elevation, 0. Well radius, 0.255. Drain angle, 0. Fracture model, let's say finite conductivity with number of fractures, 7. And then fracture half length, 300 feet. Fracture height, 50 feet. Fracture midpoint height, 25. With, let's say, we maintain or we keep this default value, fracture porosity 0.5, angle this, ZW 25, length, yes, 1000. Location, input wellhead. Yeah, we can leave it as it is. And then for the geometry and properties, perforation, okay, we put the perforation 1, let's say 3302. I'm going to change it. Or yeah, maybe it's, by the way, it's by the way calculated, so no problem there. And then wellbore model, constant wellbore storage, this, okay, good. Bottom hole measured depth, bottom hole MD, okay, this, good. All right, and then what else? Maybe we can input, yeah, this is the value that I input, so we can click on okay. So this is our well. All right. So that's pretty simple, right? You can also make contour, like for example, like this. Make it as a closed reservoir there. Okay. And then you can maximize and pan like this maybe. Or maybe we can, you know, make it looks like circular shape. So first you know, hopefully we can change a little bit, touch and reshape. Let's make it maybe a little bit more elliptical. All right. Hemispherical? No, it's elliptical, sort of. Okay, so that's it. You can lock and unlock, by the way. You can also check the grid. Or maybe we can do the grid setting later. You see there, right? Click on OK. Yeah, if you're interested, I will show you again. So you can set the background grid here. Hexagonal currently. Angle, PV max per layer, and then horizontal progression ratio. Okay. Okay, so from here, what else? We can set the geometry. Geometry input here, top plus end thickness, top constant, and we set it at 3250 with thickness constant. Make it simple, 50. Click on OK. All right, so that's it. From there, after you make the map, we can go to analysis and numerical design. All right, so now let's do something about it. Generate numerical test design. Okay, now let's review it again. Modeling type, simple, finite conductivity, 7. Number of fractures, fracture half length, this, okay, the same. Fracture conductivity, maybe we can dig it a little bit. Fracture height, okay. Fracture mid height, okay. With this, fracture porosity 0.5, okay. Fracture conductivity, let's say it's 2500 instead. Fracture angle 90, ZW 25, well length 1000. Okay, we can keep it. Include constraints. Okay, so minimum bottom hole pressure constraint, this one, minimum or maximum bottom hole pressure constraint at injector. Doesn't matter, by the way. Okay, you can also input like this or no. Okay, sorry. Oh yeah, sorry. Let's make it 15,000 instead. Okay, so for the skin 0, initial reservoir pressure. Now let's impose the value here. It's 1,150, let's say. Homogeneous, let's start with homogeneous. Transmissibility, okay, let's say 100 millidarcy foot. Permeability, okay, we can go down. Permeability, let's say 2, and then thickness 50, and then porosity 0.23, net to gross 1, anisotropy, horizontal permeability with, or Z permeability, vertical permeability versus radial permeability or horizontal permeability. All right, that's it. And then we can also input the data for wellbore storage. It's 2, tested volume, closed chamber, fluid compressibility 0.005, wellbore storage 0.01. Yeah, you can also input the test chamber. Okay. Click on OK. All right, so we can also input the history, for example. Let's say we know the history of our, our well tests. We forecast maybe, we model, and we get the prediction for oil rate, gas rate, and water rate. You can input the data, the prediction here, and you test to see what the pressure transient would be. Okay, so I'm going to copy my data and paste it here. Okay, so I'm going to load or maybe cancel history, add, check the gas and water, ensure the unit is okay. Oil stock temperature per day, gas MSCFD, water this. Okay, good. Sorry. We need to make like this. So let me count my value vertically. So I have 23 like this. I'm going to copy my data. Hopefully I can paste it here. Okay. Not yet. Not yet. Yeah. What about blocking everything here? Sorry. Okay, let me try this. Want to ensure. Yeah, I have 23 data or 23 rows vertically. Copy. Okay. All right, so I'm going to paste it manually then. So after 185, okay, so 23. So let's delete this, delete everything here. Okay, 23. So click on OK. All right, and then let's just see time stepping. Okay, good. numerical setting, use custom setting. Okay, and then not yet for impose P, not yet for output. And let's see if we can generate the case. Okay, that's the story plot. Still generating the model. That's our beloved case. Okay, so you might expect that it will take significantly longer time compared to the analytical modeling, but at least we learn about the numerical modeling, numerical pressure transient analysis. Still generating 60%. All right. Hopefully we can, we get a good result. Okay. All right. So we have the calculated, the pressure profile. So this is the 3D plot. Okay, still at original pressure, constant thickness. And you see here we have 1, 2, 3, 4, 5, 6, 7 stages. Okay. All right, so now let's extract delta P. Okay. Yeah, let's check the buildup just to see it. Okay, you have this, this pressure and pressure derivative, the log-log plot, and also the semi-log plot. Let's do the numerical modeling. We maintain all these parameters, of course, and let's generate. Because this is an ideal model, the model created by software, hopefully, when we run the numerical modeling, numerical PTA, we can get perfect match. You see here, for the history plot, you see we can, for now, very accurately match the data. The data here means something that is produced by the design. Okay, so you need to differentiate between the design and the modeling. The design is, it in this case represents the real data. Let's say you perform well test data. This is the data that you have. This is the, flow rate that you have. This is the pressure that you measure. And then when you perform modeling, you try to match the model with the design, with the data. The data here comes from the design. So you can see here, because the design is created by software, so it's not the real data. You can see it's very easy to get, good match. All right. So it's very easy to match, but it's going to be quite different if you perform analytical, because at some point, analytical, it's not the same with the numerical. The result, right? The result from analytical, might not be the same with the numerical. Although in numerical, if you click on that, you can reset from analytical. But analytical cannot reset the data or the parameters from the numerical. It can only take information from diagnostic. And I don't think we need to perform diagnostic analysis for our case, because it's, by the way, it's an ideal model created by the, the software. So lastly, I'm interested in looking at the pressure profile over time. Okay, so let's go to the first time step, initial one, and then okay, let's here, by the way, you have 3D. You can also change it to 2D X, Y, right? or pseudo 3D. 3D. So I'm looking at the pressure. Of course, the K, permeability, porosity, net to gross will be constant, but pressure will be dynamic. So let's play. It's not really obvious. Okay, so yeah. Sorry, I reduced the opacity. I thought opacity is like time step. No. Opacity is for the coloring here. So if I want to move the time step from the latest to the initial time, I should use this time step. Human error. Okay, this. So initially, the color is red at initial pressure of 1150. So now let's play. You see, we have low permeability reservoir, so that's why there is significant pressure drop at the fractures. But the surrounding area still have, more or less the same initial reservoir pressure. But close to the well, close to the fractures, you have excessive pressure drop because poor connectivity, poor permeability, poor flow capacity. That happens if you have tight reservoir. Okay, so I think that's it. I think that's all. So in this rather short series, we learned about numerical pressure transient analysis using Kappa Sapphire software. So hopefully we can learn more about this numerical exercise, but until the next video, see you and thank you.